Video 5, we're going to cover our last chi-square test, which is called a chi-square test of association, or it's also called a chi-square test of independence. Now, good thing is, this test basically does all the same math as the last chi-square test, the test of homogeneity. The only thing that's going to be different about a test of homogeneity versus a test of association or independence is in how the data is collected and in our hypotheses. So, two-way tables can arise in several locations. The cocaine study, which was in our last video, it was an experiment that assigned 24 addicts to each of three groups. Okay, we had our desipramine group, our lithium group, and our placebo group. So each group is a sample from a separate population corresponding to a separate treatment. Okay, so they kind of fixed the amount of people who were going to be given each treatment. They had control over that. The study design fixes the size of each sample in advance, and the data record which of two outcomes occurred for each subject. Either they relapsed or they didn't relapse. The null hypothesis of no difference among the treatments takes the form of equal proportions of success in the three populations. We wanted to know if those that were on the desipramine, those that were on the lithium, and those on the placebo pill, if they all had equal chances of not relapsing on cocaine. The next example illustrates a different setting for a two-way table. Okay, so this was all last video when we did a test of homogeneity. We wanted to know if, multiple treatments were all the same. So we fixed the sample sizes in each. Did they all have to be 24, 24, 24? No, they didn't have to be, but that's ideal. But we decided how many we were going to put in each group. Now, here is another way of looking at it where we don't have control, where we don't fix things in advance. So in this example, it says, in a study of heart disease in male federal employees, researchers classified 356 random subjects according to their socioeconomic status, or SES, and their smoking habits. Here is a two-way table that summarizes the data. Okay, so they took these 356 people, these male federal employees, and then they started dividing them up according to their smoking status, current, former, or never, and their socioeconomic status. So notice that, we don't have the same number of, upper class people, middle class people, and lower class people. We don't have the same number of current smokers, former smokers, or people who never smoked. It just happens to work out to be this way. Could it be that we end up with, two groups that have the same total? We could, but chances are we're probably not. So a two-way table does not compare several populations. Instead, it arises by classifying observations from a single population, which is our male federal employees, in two ways. And the two ways that we are classifying them is by smoking habit and by socioeconomic status, each of which have multiple factors. So the question we might ask ourselves is, do these data show a statistically significant relationship between socioeconomic status and smoking habit? So is there a connection between your class in society and your smoking status? So what we might look at is breaking up, we could look at, in this way we took low, middle, and high socioeconomic status, and we looked at the percent of people who currently smoke, used to smoke, or never smoke in each class. We could also look at it in terms of, out of all the current smokers, how many are low class, middle class, upper class? Out of all the former smokers, how many are middle class, upper class, lower class? And out of all the people who never smoked, what percent of them are current smokers, former smokers, or no, high class, middle class, lower class? So it depends. You could go either way. Okay, you're going to get the same type of information here. So I already have these three bar graphs made up for us, or these three histograms, I should say. Well, technically they should be bar graphs. There should be some spacing in between here, because we can flip around these bars and it really doesn't make any difference. So some things I want you to notice. The percent of current smokers as socioeconomic status increases. So notice I already have it from low to middle to high. So we're getting, upper, more and more income, if you will, the further we go to the right here. So if we just focused on current smokers, notice if you're in a low class, if you're in the lower class, there's over 45% of people who currently smoke. If you're considered middle class, it goes down a little bit. Now we're somewhere between 40 and 45%. And if you're considered upper class, people who currently smoke, now we're down to about 25%. So as socioeconomic status increases, what happens to the percent of our current smokers? It decreases, it goes down. So there's kind of a negative association here. That as one goes up, the other goes down. So now let's examine percent of former smokers as socioeconomic status increases. So former smokers, here we are at about, what, 30%? And then it jumps up to, what, about 40% there? And then it goes up even a little bit more. So as socioeconomic status increases, the percent of people who used to smoke goes up. So now there's a positive correlation or a positive association between former smokers and socioeconomic status. Okay, so this suggests that higher socioeconomic status smokers were more likely to quit smoking. And why might that be? Well, to quit smoking, you could just stop smoking altogether. You go cold turkey, but from what I hear, I have no experience in this, that's kind of a hard thing to do. It takes a lot of willpower. So how can you stop smoking? Well, you can take medication, you can buy patches, gums, but that stuff's pretty expensive from what I hear. So who can afford expensive medication? Rich people, people who are considered upper class. So people who are lower class, they may not have the same chances because they can't afford the medication to stop smoking if they really wanted to. Number 3, the percent of people who never smoke is highest in which group? So people who never smoke, let's see. In the low socioeconomic status, we're looking at about, what, 25-ish%. In the middle class, we're under 20. And in the upper class, we are over 30. So the percent of people who never smoked is highest in the high socioeconomic status group. But the middle socioeconomic status group has a somewhat lower percentage than the low socioeconomic status group. So there isn't a consistent direction here. It's not that it's consistently decreasing or consistently increasing. So there really is no correlation here, no association. Overall, the percent suggests that there is a negative association between smoking status or between smoking, not smoking status, but smoking and socioeconomic status. And what we mean by that is we're really only focusing on our current smokers, people who do smoke. Most people smoke are in lower class, and as your socioeconomic status increases, you have fewer and fewer people that smoke. So the chi-square test of association or independence, it assesses whether this observed association is statistically significant. So we might ask, is the socioeconomic status / smoking relationship in the sample sufficiently strong for us to conclude that it is due to a relationship between these two variables in the underlying population and not just merely due to chance? Okay, so our hypotheses will look like this, and you just write one of these two things. You don't write both. You either state in your null that there is no association between your two variables, and there's always just going to be two variables. That's it. So there's no association between, and then in context write what your two variables are. Versus alternatively, that there is an association between those same two variables. Okay, so that's one way to write your null and alternate hypothesis. The other way is using, instead of the association term, using the independent term. You can say socioeconomic status and smoking status are independent of each other, that they have nothing to do with one another. They're completely independent, aka that there is no link, no association between them. Versus alternatively, that they are not independent, that they do depend on each other, that there is some connection, some association. One thing that gets people tripped up is if you want to use the association route, your null uses no. Okay? But when do you use no in the independent example? In the alternate. So the no, the negation part, happens in opposite places, depending if you want to use association versus if you want to use the independent route. So whatever method, whatever word you want to use here, association or independent, make sure you're putting the negation in the right spot. Conditions, same as they have been all along, are three: random, independent, and large sample size. So random, it said there were 356 random subjects. Independent is the population at least 10 times their sample size. Well, the population is all male federal employees, and is that greater than? We have 356 as our N. So can we assume there are more than 3,560 male federal employees? Sure, we can assume that. And then large sample size, are all expected counts at least 5. Now, I know in previous videos I've always said, we're going to come back and check this, and then I never remember to come back and check it. So I'm going to try my best to come back and check to make sure that we really have what we need to have here. Okay? So now, the calculations. We're going to do this on the calculator. Okay? And I'm going to show you exactly what you need to do. And this will kind of be basically the shortcut way, so you don't have to do all the amount of work here. You can have the calculator really do most of the work for you. Now, in order to do this, we're going to need to use matrices in our calculator. So on my TI-84, if you go to matrix, which you have to use the second key, and then go 3 more buttons down to the x to the -1 power, and you should see matrix. So then what you're going to want to do is go to matrix A, but you don't want to click enter yet. What you want to do, currently it says names. You want to scroll over to edit on matrix A. Now, what size matrix do we need? Currently it says, I'm pretty sure it say 1 by 1, or maybe it doesn't have anything. I already have something in mind, so I don't really know what it says as default. But matrices are row by columns. So how many rows do we have? We have 1, 2, 3 rows. And then how many columns do we have? 1, 2, 3. So we have a 3 by 3 matrix. So punch in 3, press enter, 3, press enter, and then it takes you into the matrix. Ooh, into the matrix. Did you take the red pill or the blue pill? Oh, you know what, it would have been epic if I would have highlighted this in blue instead of green and been like, take the red pill, take the blue pill. I don't know which one. Now, in your matrix, you need to put these 9 values in there. So if I go 51, press enter, it'll take you to the next one over. 22, enter. 43, enter. 92, enter. 21, enter. 28, enter. 68, enter. 9, enter. 22, enter. Okay. So we're going to put our observed values into matrix A. Now what you need to do, press second quit, which is the next button to the right of second, which is in my calculator the mode button. You need to go back out to the main screen. Okay? And then we're going to go to stat, press the stat button, over to tests, and then it might be easier just to press the up button. And then for me, in my 84, it's C, chi-square test. So go to there, and it says observed, it should already say A, and expected, it should say B. So if that's okay, then press calculate, and then it's kind of jumping ahead of us. But we need to go back and fill in some blanks to get full credit, okay? So right now it tells me chi-square is 18.50974136. P, my p-value is 9.8082363 times 10 to the -4 power. It gives me my degrees of freedom as being 4, which we need to discuss really how to get those degrees of freedom. So it really, you can already tell with such a low p-value, you're going to reject the null hypothesis. Okay, but what all are we going to need to put for credit? First, go back to matrices where it says names, that first part there. Now matrix B should say 3 by 3. So go ahead and press enter when you're on B, and it'll say B on your home screen. Press enter again, and now, if all you have to do, don't press anything, you can press your left and right arrow keys, and you can see what all 9 of your expected numbers were. So the top left corner, if we go 2 decimal places, should be 68.75. Now you're going to need to fill in an expected value table here. So you will still need to do this. Luckily, the calculator is going to do all the work for us, and that is fine according to the AP Stats exam. So go ahead and fill in the first three you should see going down this first column will be 68.75, 83.57, 58.68. And now you might need to scroll over with the right to see the next column of numbers, 16.94, 20.60 technically, and 14.46. Keep scrolling over, and there's our last column of data. So 30.30, 36.83, and 25.86. And there's all of our expected numbers. Okay, so far so good. Now, the O minus E squared divided by E part. Are we going to have to get all 9 of those numbers so that we can add them up and get our chi-squared? Fortunately, you don't, but you do have to put a little bit amount of work here. Here's what you're going to need to do. We're going to have to do the very first O minus E over E part, which if I clear some stuff out here, we're going to pretend like we did all this, but we really didn't, because we already know what the chi-squared is. We got it earlier. It was that 18 value. So we're going to take the first observed number, which we're going to call this one, this 51. And here's its expected value. So here's what we're going to write. We're going to have chi-squared equals, and then we're going to go O minus E, so 51, minus 68.75 squared, divided by expected 68.75. Plus, now here's the thing. Screw the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth. We're going to just replace it with ... And then we're going to do the last entry, which will be this with this. So O minus E squared, so it'd be 22 minus 25.86 squared over 25.86. And that comes out to equal what you got in the calculator earlier, which hopefully you wrote down. If not, here it is, 18.5097. So you can have the calculator do all the dirty work for you. This is the minimum amount of work you have to show to get full credit. Okay? You don't have to do all 9 O minus E squareds over E. You just have to do the first and the last and put plus ... plus in between right here, so that it's like you're really doing it. You're showing me and you're showing the exam graders that you really understand how the chi-squared statistic is calculated. Okay? So now we want to find a probability that we find other chi-squareds that are greater than our 18.5097. So we have chi-squared CDF from that to infinity. Degrees of freedom, the same as they were for tests of homogeneity, which is row minus 1 times column minus 1. Well, we have 3 rows and 3 columns, so that's going to make this 2 times 2, which is 4 degrees of freedom, which I have here. And here is that very small p-value that the calculator even gave us. I just chopped off a bunch of the digits. So point, and I didn't write it in scientific notation. So this is obviously less than our alpha of 0.05, which means we're going to reject the null hypothesis. We also need to draw in our chi-square. Now with 4 degrees of freedom, it's still going to look pretty skewed right. So maybe we have something that looks like this. We know we're going to end up with a very, very small p-value. So we should be right on the tail end here. So let's just kind of barely shade in this end. We'll call this right here 18, I'll just call it 18.51. And that's it. There's your picture you need. So here's the probability statement. Here's the calculator command. Here's the picture we need. There's the p-value. There are the 4 parts that you need to do after you get your chi-square test statistic here. So now, conclusion. We have enough evidence at the 0.05 level to conclude that there is an association between smoking status and socioeconomic status. Or you could say that we have enough evidence to conclude that, how else could we write this here? To conclude, we'll say ... To conclude that SES and smoking status are not independent. You pick which route. If you want to use the association route or the independent route. Okay, just know one of them is going to have a not, a negation in it, and the other one is not. So here is the problem that I want you to do as homework and bring to class. And I will check this for a grade, and we will go over it together. Okay, so I have more information in your notes than what I just have right here. So there's more to this problem than just this. If you're reading this and going, I have no idea what this really means, there's more in your notes. I just could not fit it all on this slide here. So good luck, and we will see you tomorrow in class.